built some big generators, DC generators. He was a DC man, that's what he liked. So he would build a power station generating DC. So he would, he'd had his DC generating power station. Now, in those days, it was very difficult to convert a DC voltage. So whatever voltage you generated at, you would have to actually be supplying the person, the consumer, at the same voltage. Now, okay, a few things to cover here. Okay, so the major drawback is that we cannot convert voltages. So if you've got something generating at 200 volts DC, you can't go, oh, I'll just convert that to 400 volts or 1000 volts DC, because it's very, very difficult. And in those days, it's virtually impossible. Now, we've done already that V equals IR, voltage equals current times resistance. So if you have a certain voltage here, and then you have a wire going to your consumer, your happy consumer, so you're supplying them some load. Now, what you have is current flowing from the supply, the generator, down through to the load. Now, this cable is actually not a perfect cable. There are no, well, there are superconductors, but we don't make cables that often out of them. So generally, this is a bit of copper or aluminium, whatever. Now, any cable will act as a resistor. So this actually is the same as a big resistor, and the longer it is, the more resistance there is. What was happening is, because V equals IR and power equals IV, watts or power, we know that we can replace in our voltage there, so we know that power, this is the same as power equals I squared R. Okay? So we know that the power is related to the square of the current multiplied by the resistance. If there's any small resistance in here, and this is quite a big load, we have high current and a resistance. So we actually lose a load of power in this cable. So this cable will heat up over its long length. So basically what we're saying here is resistive losses restrict the length of these cables. What was happening is Edison, the voltage that he was generating, which is up to about 400 volts DC, the maximum cable length he could do was about 5 miles. What happens is, as you get further and further away, to reduce the resistance, you have to make the cable bigger and bigger and bigger. So he was getting to a certain point where you just couldn't make cables bigger, it wasn't worth it. So what he was doing was building loads of little power stations with rings out within 5 miles and supplying people. That's what happened originally. That happened here in the UK, it happened in America, lots of places. But every one was slightly different. So someone was generating at 130 volts, someone was generating at 400 volts. So you'd have to have all your stuff would all have to be locally manufactured to the local voltage. It would have just, it's a nightmare, real nightmare. Now, Nikola Tesla, crazy guy but very clever, came along with using the concept of alternating current. I haven't actually gone through what direct current and alternating current is, have I? That's true. Direct current, if you were to look at it over time, would just be a straight line. Alternating current would vary in a very terrible sine wave. So direct current is just a constant. Alternating current varies over a zero value. So that's 0. In this case, that's 0. So direct is just constant. Alternating varies. In the UK, it varies 50 times a second, 50 hertz. In America, it's 60 hertz. Generally about that. Now, what Tesla saw was that you can very easily generate AC power from a rotating generator. And he also knew that you could convert AC from one voltage to another using a transformer. Transformer's very robust relatively easy to build technology, and they knew how to do it. So he proposed using alternating current, where what that means is you can convert your voltages to transmit them at a very high voltage, therefore the current is very low, therefore the resistive losses are very low, therefore your wires can be much smaller, much cheaper, you can transmit miles and miles and miles. Our system in the UK transmits at various voltages around the UK, up to 400,000 volts. That's our super grid is at 233 and 400,000 volts. And then you convert it back down to a usable voltage, so you don't really want to be plugging in 400,000 volt plugs. So we convert it to 230 volts in the end, using transformers. So the high voltages means you can carry a lot of power very long distances with very low resistive losses. And that's the basis of our national electricity grid. And again, watch that TV programme if you're really interested in it.
What's the name of the TV programme?
I think it's called The Secret Life of the National Grid. That's right, The Secret Life of the National Grid. I haven't actually seen the last ones of it. So, standalone power supply systems, what are we talking about? So, I'm probably now going to look more at actual small systems, standalone power supply systems. People call them lots of different things. People call them off-grid systems, people call them mini-grids, people call them 12-volt systems, loads of different names for it. The term that generally is used, certainly the academic term, is standalone power supply system. They are generally based upon a single generator or a few generators, and it's physically close to the load, so relatively small systems. You don't have a high voltage, you don't have long transmission systems, so you're generally using lower voltages. Although there's no actual distinction, like you could say that the national grid is a small standalone power supply system compared to the world. So there's no actual clear distinction of what is a standalone power supply system and what's a national supply grid. Generally, we're talking ones and tens of watts up to tens of kilowatts. When you get bigger than that, it's better to push lots of things together. So my research before was on the higher end of this. I was looking at 50 kilowatts of wind turbines on a system. Actually makes the challenge a lot harder because you've got quite a lot of power to deal with. Why would we use one? This is a place I went to in the Philippines. This is Lamag in the mountainous region of the local Sur. And it's pretty remote. It's 2 hours walk from the nearest town, across a river twice. Yeah, so it's pretty difficult to get to. So no one's going to go, hey, there's 400 people living there, I'll give them electricity. So no government is going to go, I'll build the electricity grid to there, because it's just not economic. It's just not worthwhile. So it's uneconomic, just doesn't make sense. I have seen, I wish I had a photo, I've seen a system where they had high voltage transmission lines going pretty much straight over the community, but the community itself was using microhydro system because it was uneconomic for the government to put in a transformer to supply that one village, even though electricity is going straight overhead. It's just how things happen. It also could be where national grid doesn't exist, so we're talking about islands, small island systems. There's loads of reasons to use a standalone supply system. For this talk, I'm going to focus on community power supplies for developing countries, but the principles are exactly the same for every system. Some facts and figures about electricity. About 1.6 billion people don't have electricity to a reliable electricity grid. Generally, they're in developing countries, not all, there's some island communities. To supply that, generally people use local standalone power supply systems, and they're generally based on diesel generators.
That one says SPAs, not SAPs.
Sorry? Oh, spas, yeah, majority of spas. It's just nicer to get your feet done and manicured. Depending upon the size of the load and the distance to national grid. Oh yeah, so there is a certain point at which the cost of installing a transmission line from national grid gets higher than the cost of installing a renewable energy system or a standalone power supply system. Diesel generators, very cheap to put in, so that's why they're used, but long-term costs